Good morning, everyone. I'm Giorgio Veronesi, President of the European Federation of Chemical Engineering, EFCE. I've been in the board of EFCE in various positions for almost 9 years and currently in my second term as president. I'm a chemical engineer by training, graduated in Padua, Italy, and I've been spending the whole of my career in the engineering construction business, involved in many projects around the world with several assignments overseas. I'm very happy to be introducing this webinar on multiphase flow in gases and liquids about similarities and differences of particles and bubbles in gases and liquids, a very technical theme. Let me say something about the Spotlight Talk series. This is now our fifth year of the Spotlight Talk initiative, which started in 2020 to keep together the chemical engineering community during the COVID pandemic. The success of the previous years convinced us to transform the Spotlight Talk in a regular feature of EFC program. And now we have two series in even years, spring and autumn, and one series spring in odd years, where we are holding the European Conference of Chemical Engineering in autumn. So let me take this opportunity to remind you that next year, 2025, the ECI-ICAB conference will be held in September in Lisbon, an event not to be missed. This fall, 13 of our working parties and sections, sustainability, mixing, electrochemical engineering, high-pressure technology, food, loss prevention and safety promotion in the process industries, agglomeration and multiphase fluid flow, this one of today, static electricity in industry, education, polymer reaction engineering, thermodynamics and transport properties, and early career chemical engineers are delivering over 2 weeks a short session of 3 or 4 talks focused on specific topics by leading industry and academy experts. This webinar today is managed by two working parties, agglomeration and multiphase flow. This is it's a very nice opportunity for us to have two of our working parties cooperating together in this webinar. The complete program of the Spotlight Talk is available on EFC website. EFC promotes scientific collaboration and supports the chemical engineering activities in 30 European countries, representing more than 100,000 chemical engineers in Europe. And the EFC working parties and sections cover all major specific aspects of chemical engineering and are, in fact, the core of the organization, forming the scientific engine that drives many of EFC activities. They provide an important forum for technical exchange and networking among chemical engineers in Europe. So before concluding this short introduction, I would like to thank all the people who work hard inside the working parties and section and EFC in general for this initiative to happen and to be successful. In particular, I would like to thank very much Martin Pou of EFC Scientific Secretariat in Toulouse, who did most of the conceptual setting up and practical activities. I thank you for your attention and wish all the speakers and the attendees a fruitful and successful webinar. I would then give the floor to Professor Stefan Heinrich from Hamburg University of Technology, Chair of the Working Party Agglomeration, to introduce the works. Please, Stefan.
Yeah, dear colleagues, dear friends, it's a great honor for us to give this special session today, and it was the original idea of Michael Schlüter, who is a chair of the Working Party of Multi. With liquids seen during the last many years, and that was a starting point. And needless to say that we have many novel techniques, modern simulation techniques. Also we sensors, we have also measuring techniques, novel in situ and in situ techniques, sometimes also magnetic resonance imaging plays an important role. So, and also the modeling aspects are very similar. And there next many years. Yeah, and I would like to give also the word to Michael, who has some interesting comments on that topic. Yeah, perhaps Michael can also.
Yeah, thank you so much, Stefan. Also from my side, welcome and hello, everybody, to all our colleagues and friends. We are very happy to have this opportunity by the EFCE to give this spotlight talk today. And yeah, as Stefan already mentioned, we are here colleagues at UHH in Hamburg and also good friends. And we are supervising a lot of master theses together. And always we are thinking about bringing these two topics together because interestingly, as you probably know, agglomeration and multiphase flows, gas liquid flows are more or less totally separated disciplines, despite the fact there are a lot of similarities. And so we are very happy that we are able to attract so valuable speakers today and so international well-known experts to hear about their latest results and their newest achievements. And with that, and with having in mind that there might be similarities between solids in gases and bubbles in liquids, let's talk about that the next hours. And by the way, as you might know, it's not possible to ask questions by yourself orally. You need to write down the question in the chat. Yeah, we will collect the questions and we will ask the questions after each presentation. And the answers can also be given by text messages during the next talk. Yeah, so please ask your questions via the chat. And further on, we will have a discussion after the last presentation, what we have learned from each other and what we can learn from each other, and maybe where we have opportunities for collaboration and maybe joint projects. So with that, thank you so much so far already, and we are very much looking forward now the first presentation, and this will get given by Stefan Pirker from the Johannes Kepler University in Linz in Austria. Thank you so much, Stefan, for doing that, and enjoy the presentation.
Hey, so I hope you can hear me and you even see my screen. Is this okay for you?
Yes, perfect.
Perfect. So then I just start, and I would like to jump into my topic by some personal slide. So the next slide, if I'm able to proceed. Yeah, the next slide, you see a picture out of my PhD thesis. It's from the last century. And in this PhD thesis, you see a lot of elements of bubble multiphase flow. So these are bubbles up here, bubble blooms, and they are kind of introducing a recirculation flow. And these clouds here kind of mimic the transport of some species. And this was done with Fluent. And at that time, Fluent was written in Fortran, and we performed the simulation on a structured grid. And you know, we at that time we did not have any model to really model the free surface, so we have to deform the grid accordingly to model it. Then about 14 years later, we modeled a similar process. This is a copper converter actually, and if I start the simulation, you see a lot of things has changed. So you see this thin layer of slag, you see the free surface, which is now modeled with a VOF model, and Fluent was migrated towards a C language code on an unstructured grid. So a tremendous development has occurred during slightly more than 1 decade. So, but if we look at it from a different point of view, then we see, okay, also the model portfolio has improved tremendously, and also the resolved spatial and temporal resolution has increased tremendously. Those simulations are way beyond real-time capable. So they can be considered as slow and offline digital models. And you know, if we would like to achieve what is written in the title of my presentation, So from slow offline simulations to online digital twins of industrial processes, we have to use completely different approaches. So we have to kind of go away from this purely equation-based approach towards some data-assisted approach. And this is the topic of my today's presentation. So I've organized this presentation in two parts. In the first part, I would like to introduce the concept of recurrent CFD, which is one of the possibilities of data-assisted simulations. And in the second part, I would like to showcase an industrial application, because I've heard that this audience is more on the industrial side. So let's jump into the topic with the first introduction. And on this first slide, this is one of my standard slides I'm using since 5 years. You will see bubble columns and fluidized beds side by side. So I try to get some. Do you see my mouse?
Yes, it's visible. No problem.
Okay, thank you. So if you look at different types of flow, you often can observe reoccurring flow patterns. In bubble blooms, there might be clusters of bubbles, or even the whole bubble bloom is oscillating regularly. In fluidized beds, we have this voids, which are these bubbles in the fluidized bed, which appear regularly. So we have reoccurring structures. For the sake of simplicity, I would like to focus now on the meandering bubble bloom. So if we have a closer look on it, so one of my PhD students did some simulation of it, and we could actually reproduce this meandering motion quite nicely by full equation-based CFD. If we now consider reoccurring flow structures, then the central question would be, when can we consider a flow situation being similar to another flow simulation? And a core mathematical core criteria is this recurrence norm. So in this recurrence norm, we integrate over the whole volume and look at, for instance, in this case, it's a field variable of the volume fraction. So if the bloom is on the right-hand side, then this integral will give a low value. If at another instance of time, it's always also at the right-hand side. And we could also picture this by a recurrence matrix. In the recurrence matrix, we compare the flow situation at different time steps with flow situation at another time step. Quite naturally, the diagonal is 0, because if you compare a flow situation to itself, the recurrence norm would be 0. So if you restart this movie, then we see that the recurrence matrix, the corresponding recurrence matrix, also changes from a chaotic off-diagonal situation to this kind of stripes. And in these stripes are a sign for reoccurring flow structures. So a pair of flow situations between this time step and this time step gives a bluish off-diagonal situation, which refers to a good agreement of these two pairs. And the red one would be a bad agreement. This would be if the bloom is just on the other side. Now we could exploit this similarity in order to construct an artificial flow. So we just start by replaying data we have obtained before for sequence 1. Then at the end frame of the sequence 1, we just look for a similar frame. In this case, the similar frame is in the past of our database. Then we stitch together, we proceed with the second sequence. And at the end of the second sequence, we look for a similar frame and so on. So we could kind of extrapolate the flow beyond the time span of our database. And if we have done this, we have the velocity field available, we have the field of volume fraction available, and on top of this, we could trace some species concentration, for instance. And in this numerical experiments, we have one in injection side and one probe just above it. And you see here two lines nearly on top of each other. The one is the full equation-based CFD, and you always see two peaks because the bloom just passes the probe and then immediately goes back. And the two colors refer to full CFD and this data-assisted recurrent CFD. And they match very, very well, and we got a speed up of 2 orders of magnitude. What I've described here is labeled flow-based rCFD, and the second flavor is this transport-based rCFD. And in order to explain the transport-based, I invite you to Linz, to my hometown. There's the river Danube, and if you look down to the river Danube, you see something like this. So there's a shear flow at the pillar, and if you just imagine to throw some white color into it, then this white color will be affected by fluid flow, so it will move a little bit like this. And from a fluid dynamic perspective, we could decompose this flow situation into convection and diffusion. So we all know that there is a mathematical fundament for this kind of flow, which is by Navier-Stokes, and typically we apply a computational grid in order to solve this Navier-Stokes equation, in order to describe this propagation of this white color. However, we could also look at the same situation from a completely different point of view. We could consider this computational grid as a network, a communication network. And once we throw in the white color, we activate one cell. And upon convection, this cell just calls another cell, the receiving cell. And upon diffusion, this receiving cell just shares its information with the neighbors. So that's a very, very crude approximation of convection and diffusion. So we shall boldly decide to replace convection by cell-to-cell shifts and diffusion by phase swaps. So this is very, very crude approximation. So how would this work? First example, it's a academic example of a fluidized bed. And here we consider mixing. So this was work done by Firas. And what you see here are two animations. On the left-hand side, it's full CFD, equation-based CFD. On the right-hand side, it's rCFD. And in this case, it's in the replay mode. So we just replay the sequence of data frames from the first to the last. So we do not perform stitching in this case. So let's see how this compares to each other. And very, very surprisingly, you nearly see no differences. You have to be very careful to see any difference. And in this case, once again, no transport equation is solved. It's just cell-to-cell shifts and phase swaps. And due to this simplicity, the simulation time dropped from more than 3 hours to just 9 seconds. If we go to this stitching, this artificial stitching, then the situation changes because now we cannot perform a one-to-one comparison. But even so, we can look at the mean color, so at the mean mixing. And you see that the reddish just migrates to greenish overall. And we could assess the mixing index. And this is done in the right-hand figure. And you see that all these black curves for full CFD and all these red curves for rCFD nearly lie on top of each other. And at the same time, we have achieved a speed up of 4 orders of magnitude in this case. Okay, so I really roughly introduced the concept of rCFD and also addressed mixing in fluidized bed. In the next couple of slides, I would like to talk about segregation in fluidized bed, so polydispersed fluidized bed. And this was work done with Stefan Heinrich, Heinrich's group. And, you know, typically if you perform such simulations, you would use DEM maybe, and then you get at such simulations. There are red particles, which are larger, and blue particles, which are very small. And you see an accumulation of these red particles at the bottom of the bed and vice versa and on the top of the bed. So this is the modeling tools exist for this, but the simulation times are really beyond real time. So we need 15 hours for 1 second of process time. So we have thought about, could we picture the effect of segregation with rCFD? And this is still full CFD DM. And if we look at the mean coordinate of gravity, center of gravity, then you see such curves. So we artificially let the bed collapse, and then there's a bubbling motion. And you see 4 cases, so 2 velocities and 2 bed inventories. So very wide distribution, very wide difference between the large and the small particles, and kind of lower difference, smaller difference. Now, this is the mean bed height. And if we look at the bed height of individual particle fractions, we see segregation. So here you would see that the larger particles indicated by the dashed lines, they kind of migrate to a lower vertical coordinate, while the smaller particles do the opposite. So in this case of the small difference of particle size, this is will eventually proceed into some steady state, while in this case we will face defluidization. So how could we model this in the framework of data-assisted rCFD? So we thought about introducing a drift velocity for individual particle fractions. The drift velocity should depend on the difference between the diameter of the particle fraction, so small or large particle, to the Sauter mean diameter. And the difference squared times an empirical constant gives us a drift velocity. And we further implemented this drift velocity as directional phase swaps. And if we, after implementing it and testing it, we see in the replay mode that we can reproduce the segregation behavior we have observed before nearly perfectly. But now the simulation is 4 orders of magnitude faster. This also holds for the stitching. Now, once again, a direct comparison is impossible, but by means of magnitude, we are on the same page as the full CFD-DM simulation. And this also holds for average profiles. In this case, you see the profiles after, I think, 5 seconds of simulation time. Okay, so these were kind of academic exercises. So we have lab scale experiments to the maximum. And in the second part of my talk, I would like to switch now to an industrial application. This is plotted on the right-hand side of this slide. It's from steel industry. So in the ladle, there are 170 tons of liquid steel at a temperature of 1,600 degree, more or less. And you have a vacuum chamber. So in the top chamber, also seen here, there is vacuum. And in one of these snorkels, argon is introduced. And this is a very, very complex situation because we have now argon into liquid steel, so a huge density difference. We have the expansion of the argon bubbles towards vacuum within hardly 1 meter. So these bubbles are virtually exploding in the vacuum chamber. And there is no chance to mimic this by some water-air experiments. So we have to kind of trust our simulation tools. And in the first attempt to at least get some indication of plausibility, we looked into the real plant. And there's a camera installed, and we could make POV assessment. And we could at least conclude that a Rens model would not do the job. So we need some scale resolved simulation in order to picture this recirculation flow in the end. So once we have done this, so we trust CFD, more or less, we trust this, we can deduce our database we use for rCFD, for recurrent CFD. And once we have recurrent CFD, we could look at, for instance, the distribution of titanium. So they throw in titanium here on top, and we could virtually follow the dissolution of titanium in real time. So this is a computational grid of 3 million cells, and this simulation runs in real time. So this leads then to histograms like this. So we can we can assess the heterogeneity of the steel melt over time. This is something we cannot at all obtain by plant measurements. All we can do with plant measurements is that we can take probes at a distinct position at a distinct point in time. And you know, each of these symbols here, so the red lines are rCFD and the symbols are plant trials. And for each of these symbols, a hero of validation entered the steel plant and took a probe. So this is really hard job. And at the first glance, this looks very nice. But if you have a second view on it, then you see that there are huge deviations of this point probe. So you look at this logarithmic scale. So it's hardly impossible to deduce recirculation rate just by this plant measurements. So we looked also at hydrogen, because that's the main reason for this process. So degassing is the main reason. So we have dissolved hydrogen in the steel, and this then goes into the off gas. And this degassing is triggered by ambient pressure. So the black line is the ambient pressure. This reduces in the vacuum chamber, and at some pressure, degassing kicks in, and we see, as a result of rCFD, we see the hydrogen in the off gas. So this can be compared to plant measurements, and now the plant measurements are reproducible. If we compare these two plots, we see differences. One is there's a shift. The shift can be readily explained because the measurements are way downstream of the vacuum chamber. So there is a natural shift, which is in the range we see here. And then we see that the amount of hydrogen, the total amount of hydrogen loss, it's different. And if we consider the hydrogen content before and after the process, then we have to say that the simulation is correct, and the plant measurement are just missing hydrogen by a factor of 2. So it would make sense to shift and scale the plant measurements in order to get reasonable plant measurements. And if we do this, we get this shaded curve, and we see that there are significant differences. So most probably our rCFD is not correct. But nevertheless, we are able to deduce real-time capable digital twin out of full CFD simulation of this complex industrial process. So in the last part of my presentation, I would like now to address not real-time synchronization, but uncertainty measurements management. So once again, what we have seen is the hydrogen in the off gas. So what we have done is we have a CFD simulation, which refers to a recirculation flow of 800 kilo per second. And out of this CFD simulation, we deduced a database, and on top of this database, we ran rCFD, which gives us this curve. If we use a different CFD simulation, which delivers us a higher recirculation rate, we get another database, and this other database gives us this dark blue curve, which is slightly different. So what we found out is that we get a very, very similar or even equal situation if we just use the first database and just adapt it accordingly, such that we have faster cell-to-cell shifts. So we kind of accelerate the flow without changing the topology. We get nearly the identical results for this situation. So let's go back 2 slides. So these were the slides I shown you 1 minute ago. If we are honest, that's not the situation. The situation is like this. We don't know if we have a correct CFD simulation because the system is that complex that we just don't know how to model this situation in the upsnorkel. So we deduce a database out of it, and we cannot assume that the database is correct. But what we can do is we can spread the database. So we can use this database, which gives us the main topology of the flow, and we can spread this information towards other databases. So we can actively address uncertainty. And on the fly, so during the operation of the industrial process, we compare the predictions of each of these rCFD simulations with the real measurements. So this is done with this green shaded curve. And once we have done this, we could choose the simulation which fits best. And this is the most reliable or trustworthy simulation. Once we have chosen the most trustworthy simulation, we can then look at other properties of this simulation, which would be, for instance, the dissolution of titanium at this point of time. Okay, this was a very rough presentation of what we are doing, and I would close this presentation with an outlook. So CFD simulation themselves of industrial processes will continuously improve in future. And I think this holds for fluidized bed simulations as well as for simulations of bubble bloom of any multiphase flow simulation of any turbulence simulation. And kind of decoupled from this, we can provide rCFD, so recurrence CFD, as a workflow from this purely equation-based CFD towards an efficient 4-dimensional representation of transport processes. And this is such efficient that in many cases this runs real-time or faster than real-time. So rCFD, that's the third point, runs concurrently to the industrial process. And by on-the-fly comparison to plant data, its reliability can be assessed. And once we have assessed its reliability, we can just look at a huge amount of data, and we could get valuable information, for instance, about process heterogeneities. And in many cases, process heterogeneities directly relate to product quality or to process failures, like in the case of defluidization. So I hope I'm still in time, and I would like to close this presentation.
Thank you so much, dear Stefan. It's even impressive to see how the recurrent CFD can improve things. Yeah, and this very fast simulation technique allows us to do many more, which never has been done before. Yeah, there's a first question in the chat, if I can read the question, from Professor Penn from our university in Hamburg here. Thank you for the great talk. Are there certain particle systems, for instance, flow conditions, geometries, particle types for which recurrent CFD works very well, and others for which you would not recommend the technique? Good question.
Okay. Yeah, thank you for this question. You know, recurrent CFD has this term recurrence in its title or in the name. So this is some requirement. So the particle system you have should have some reoccurring flow features. Otherwise, the concept of storing flow features and then addressing them would not work. So, but you know, this essentially holds for all data-based simulations. So also all these simulation techniques which are coming up now, they somehow rely on the fact that your trained system has already seen kind of or similar situations before. So this is maybe one answer. So I would not recommend, so it's not suitable for a situation for instance, if you have Hopper discharge, then yeah, this is not a pseudo-periodic process. And but it's also not. You could also address Hopper discharge. If you make many Hopper discharges, one after the other, then and kind of replay it, then it's possible again. So I'm not sure how strict this criteria is, but as by now, you need to have a pseudo-periodic flow with recurring flow pattern.
Yeah. Thanks. Yeah, some more questions. Next question from Alain Line, or Ellen Line. Yeah. Thank you for your impressive presentation. What is the main difference between what you call the comminution network and attempts to compartmentalize reactors?
Yeah, that's a very, very good question. So I like it very much because it's very similar. And you know, if you consider all these individual cells in a finite volume mesh as compartments, then you are kind of in a compartment model. And I don't want to do this, but uh, we are now actively working into linking rCFD into compartment models, which you then can use for flowsheet modelings, for instance. So I think this with the techniques of rCFD, you could also link full CFD to compartment models, which then can be incorporated into flowsheet models. So these are interesting questions. So we are asking ourselves the same questions.
Very nice, yeah. And also a question from Alpa Koyunchu. Firstly, thank you for this very interesting topic and presentation. Have you ever compared your recurrence CFD method with GPU-based CFD applications in terms of efficiency and pace?
Personally, I have not done this, but all I have heard from other groups, and for instance, from this group in Graz, so classical CFD is not suitable for GPU, but there are other methods like lattice Boltzmann, which are suitable for GPU and which are readily run in GPU. But also they are limited. Now we are speaking here with rCFD of a speed up in the terms of 2 orders of magnitude. And if you coarse grain rCFD, you can go to 5 orders of magnitude or 6 orders of magnitude. So I'm quite convinced that this is not achievable with any of these GPU attempts. And the GPU thing has the problem. They are good if you can send them parallel tasks, which they perform in parallel. If they have one if in between, the performance is down. And in classical CFD with arbitrary shaped grid cells and arbitrary shaped grid size or cell size, you always have this kind of if questions in between. So I don't see any chance of GPU-based CFD applications to get into this level of efficiency.
Yeah, many things. They are very interesting. Coarse graining LCFD. I never heard about this from
Yeah,
you.
I can show you.
Cool idea. Yeah? Then you are super fast. Yeah. Okay, perhaps last question, but now we are a bit out of time. Yeah? But okay, perhaps I can answer to the last question. Great presentation, or you can answer. Great presentation. Congratulations. Now the validation of recurrent CFD was performed with CFD, which has many limitations. Did you seek validation for possible very simple cases where you have as well experimental?
Yes. I can answer this. So we had a collaboration with Hans Kuipers from TU Eindhoven on the fluidized bed, where we directly compared rCFD with experiments. And this is published, I think, in 2019 in Chemical Engineering Science.
Yeah.
So this can be looked up to make it short.
Also one of the popes. Yeah. So was a good agreement. Okay. Then I would say we
we can shift to the discussion afterwards, maybe.
Yeah. We have also a podium discussion afterwards. Yeah. Then let me perhaps Yeah, I have to check if there are any other questions. Yeah, though also Michael Schlüter has also some questions, but he can ask later during the podium discussion.
And Stefan can also answer the questions. Stefan Pirker can also answer the questions just by writing down
Yes.
in the chat. Yeah. And we can refer to the. Thank you.
Good comment. Very good comment. So then it's a very great honor, perhaps, that I can introduce now Professor Frank Kleine Jäger. Frank is very well known, and after many different career steps, he is now since 2020 Vice President Solid Formulation and Handling, Process Engineering at the BASF company. And he's also giving lectures in Aachen as well as at our university on solids processing in chemical industry. My dear Frank, perhaps you can start now.
Yes, I can. Yeah, thank you, Stefan, for this very kind introduction. And it's a great pleasure for me to be here today for giving an EFCE talk. It's entitled Solids Flowsheet Modeling in the Chemical Industry. Of course, on the one hand, there will be a clear focus, let's say, on our company, the BASF SE. And I will also try to put a little more focus on, let's say, applying this solids flowsheet modeling approach to our applications at BASFs. So we are not the ones to fully develop the models. We are more the users of such tools. So this may be as a first information. Then, of course, it's a great pleasure that also I think Moritz Buchholz is in the team here in the auditorium. Moritz, he's a former employee of the Technical University in Hamburg and a PhD student there. But since quite some time, he's with BASF, and he's also today in charge of all these solids flowsheet modeling activities. And you can see that we've got quite some teams from the German universities in Hamburg, in Karlsruhe, in Magdeburg. They were involved in the development of this approach, and we also collaborated here with the DCS computing company in Linz. Okay, let's start. But before I focus on the solids flowsheet modeling, I would like to give you a brief overview about, let's say, the status of digitalization for solids at BASF. Yeah, our focus is not only on the modeling and simulation, we also put quite some effort in the generation of good data. So it's also about, let's say, projects which try to tackle sensors which are new and that are not in use at BASF. So we have, for example, some analytics and projects going on for evaluating the Parsum probe. That is one example. There are other projects where we try to come up with new sensor technology. Then data analytics and use of artificial intelligence. That's also quite some interesting topics that we are currently working on. And one example here, together with Carsten Schilder, Arno Quader from the University in Brunswick, we are working on the use of AI for tuning the morphology of our solids and for also trying to improve the process control of our unit operations, as for example in precipitation or in milling. And here we see that the outcome is quite positive, and we also see that there might be much more to come very soon. Then data engineering, data processing. Here in a collaboration with rCPE in Graz, Professor Kienast, and also in collaboration with Bayer, we are really trying to develop a prediction database and a new methodology for solids parameter estimation. So at BASF, we have got tons of data, sometimes 10, 20, 30, maybe even 40 years old, stored on different computers, stored in lab journals, typically difficult to get accessed. And here we try to come up with a new methodology that enables us to make use of this historical data. And that is then used for parameter estimation in different processes. Yeah, and last but not least, of course, then modeling and simulation. On the one hand, we also develop models for the different unit operations. Here we have own teams that do that. but more or less we try to make use of simulation tools for the modeling of solids, be it CFD or DEM, and of course also the flowsheet simulation of solids. Okay, flowsheet simulation itself, of course, is nothing new. As you can imagine, it's been developed many decades ago, and also at BASF we make use of flowsheet simulation since 40 years. So this is a slide of Norbert Asprion. He's one of our experts in fluid process engineering, and he's very deep into standard software tools like Aspen, like Hammerzin. And here we make use of these tools, for example, to improve plant operation, of course, for bare modeling, but also for simulation and optimization of our existing unit operations. And in case we come up with a new process technology and we have to make a decision for process A or B, we also make use of this simulation tool for decision making. That's quite interesting. But this has always been done for fluids, never for solids. And so with this new idea, we are trying to bring something really new into BASF. That is the flowsheet simulation of solids. Today, on the one hand, we make use of Excel, very simple process modeling tools. Here we see that we use empirical correlations. That's working very nicely. But we also, on the other hand, make use of very detailed simulation. So, for example, discrete element modeling, CFD or coupled CFD DEM, that is also used. We have these very detailed information then on the other hand. And now the idea is to bring all together. So this detailed simulation, then we have, let's say, this information on multi-scales that we want to bring into this flowsheet modeling approach, but also the information we get from the more simple process modeling. Yeah, and our flowsheet simulation approaches that we make use of such a flowsheet as you can see here. So we have the raw materials on the left-hand side, then the sequence of different unit operations, where we track important process parameters like, for example, the mass flow, the temperature, the composition, or the particle size distribution. And our target is also that we finally would like to track property functions, as, for example, the surface area of a catalyst or the tablet strength of an extrude. And this is something that we have also in mind. And we believe that this flowsheet modeling approach should enable us to do this. Of course, we need to have good models. It's a very strong model library. And this is also something where we continuously work on. Well, some years ago, we then said, let's say, based on the information we had from academia, we realized that we should be able to also come up with a new approach for the flowsheet simulation of solids. And then we said, okay, let's try and evaluate this. And we did this with the partners shown here in the top right. So with Technical University in Hamburg, KIT, then Magdeburg, DCS Computing, and the newly formed company Dissol Tech. We have set up a project that should last for 3 years. Finally, we also made a follow-up project on that. We already have 2 successful PhD works on that, and another one is ongoing. And the strategy was that we wanted to take a look at a real-world process that we wanted to mimic. And here we said, let's go for the zeolite production process. That's an in-house project at BASF that is based on, let's say, 5 process steps, from the synthesis via the solid liquid separation, the spray drying, then later to the calcination. And here we agreed that we would like to make use of the software Dissol. And what is Dissol? Yeah, that's finally an outcome of the work. And I think Stefan, Heinrich and team and all the others, they know much better. But Dissol was a product that came out of a DFG funded research work that already started 2012 and ended more or less in 2020. And it is a software that is, let's say, can be used in Windows or in Linux environment. And same year, 2020, we then started to evaluate this tool. And we wanted to see if it really gives us valuable insights into our BASF processes. We started this, let's say, evaluation later on in the year 2023. The company Disortec, as a startup from the Technical University, was generated and funded. And we also said we need to have an industry consortium that supports this further development. So companies like Evonik, like BASF, they are partnering up now, and we are still looking for others to support us here. And with this industry consortium, we believe that we will get let's say, successful software development on the one hand, but more importantly, a continuous support over the course of the next years for this software. Of course, also if we might get access to a new GUI or the development of process models. And we also see that Disortec is also strongly working on advanced features like a sensitivity analysis tool or the automatic process optimization tool. Okay, let's take a look at the process that we try to mimic. It's about the production of zeolites. These are typically materials that can be used as a catalyst or as an absorption material or as a molecular sieve. It all starts, let's say, in the reactor. Zeolites are typically aluminosilicates that have active sites that act also as a catalyst, formed in a reactor, which is typically run in batch mode. And then we hand over this product to a more continuously operated sequence of unit operations. It starts here then with the centrifuge. Here we have import, let's say we have input parameters like the mass flow, the solids concentration, and the particle size distribution that comes out of the reactor. And then we are tracking these parameters going to a nozzle where we generate a spray that is introduced into the spray dryer. And then the spray dried product with, let's say, residual moisture, but also with a residual carbon content, so with organics, is then fed to the calciner. We separate this into two parts, calciner 1 and 2. Because of this exothermic reactions of the organics, we need to split this up. And interestingly, we also have a chance to get information about the morphology of our product, for example, coming from the spray dryer. And here you can envision, let's say, donut-shaped particles, spherical particles, dense spheres, hollow spheres. And this information we can also try to track by help of this flowsheet simulation technique. And that is also something that is of interest for us as BASF. For all these different unit operations, we needed to come up with models. And here, for example, for the reactor, we need to mimic the, let's say, the nucleation of the unit cell to initial crystallites that are then transformed to zeolite primary particles, which then further aggregate to bigger crystallites. And the, let's say, concentration and the washing stage, that is the second unit operation that consists of several multi-compartment decanter centrifuges alternating with water mixes. And the drying, that is described by a co-current spray dryer model developed by applying a two-dimensional population balance approach. And you also are able here to mimic the heat flow inside the spray dryer. For the rotary kilns, a multi-compartment model was used that describes the gas-solid reaction in the countercurrent solids and gas flow inside this reactor. Okay, let's take a little closer look at the several unit operations. So first of all, here we needed to come up with a, let's say, suitable model for the precipitation process. In the first step, we tried to get information about the flow profile inside the precipitation vessel by use of CFD computations. Yeah, and finally then DEM is used to generate statistics on the particle collisions for the various values of process and material parameters to describe the particle aggregation, but also the particle growth inside these volumes. Yeah, and this information that was obtained is then used to find the individual contributions of several empirical agglomeration kernels to the overall growth and the particle size distribution. Yeah, and the found contributions later on and the variation of the process and material parameters, they are used to train a data-driven surrogate model of the agglomeration kernel, and that is an artificial neural network. But then later, the finally derived kernel, and here also here on the left-hand side, the information about the reaction kinetics, they are applied to build a population balance model that is used in the Flowsheet simulation. So that's the first unit operation we were working on. Yeah, and the second unit operation, we have a decanter centrifuge where the synthesized solids, they are separated from the liquid phase. You see the feed that enters the centrifuge via a pipe, and in the cylindrical and conical bowl, you see that a rotating liquid pond is formed, and the screw conveyor that transfers the sediment from the left to the right-hand side to the conical part. Yeah, and the centrate leaves the centrifuge over an overflow weir. Then you see that the solid liquid separation stage is described by a multi-compartment model. That was developed by the colleagues at the KIT here from Gleis et al., from Hermann Nierschel's team. And that considers on sedimentation on the one hand, but also compaction of the cake on the other hand. And if you take a look at the results, then you see that the experiments, but also the simulation, they show quite nice agreement for the sediment here, shown in orange on the one hand, but also for the centrate here in blue on the other hand. Now, to mimic the phenomenon of the spray dryer, a multi-scale and also a multi-component model, multi-compartment model was developed by Moritz at that time when he was at university. And this model that considers the different drying kinetics and also the particle solidification inside this spray dryer. In addition, we also take a look at the heat and the mass transfer, as well as the heat loss over the spray dryer wall. Then we also need some information about the flow inside the spray dryer. And here we make use of CFD simulation to get this information and hand this over to the Flowsheet model as well. It's important to increase the accuracy of the model. And here, finally, you see that we also try to get information about the particle morphology. Here we make use of coupled CFD DEM work of the single droplets. And here, for example, you see that depending on the, let's say, yeah, depending on the drying kinetics that are established, we can mimic here, for example, the formation of different morphologies. And in this case, it's a hollow sphere. And of course, having this information is, of course, of great help if you work in the field of product design. Okay, and finally, the calcination of the zeolites is performed in a rotary kiln. It is described again by a multi-compartment model that is mainly reflecting the gradients along the kiln axis. The model is based on work of Küssel from RWTH in Aachen. And here we have information on particle movement and reaction inside the solid bed, which is extracted from coupled CFD DEM simulations. Finally, you see that we have different phases inside the calciner, that is the solid phase, the gas phase, and also the wall. And here, of course, we have different heat transfer phenomena. We try to get especially information about the temperature at the inner wall of the rotary kiln, because this is mainly affecting the heat transfer to the gas and also to the solid. Well, and to get this information, we also have set up, let's say, a collaboration with the University in Magdeburg to get access to the data. And they have a nice experimental setup that is shown here. Here you have, on the one hand, fixed thermocouples that are measuring the temperatures inside the moving bed. And we also have thermocouples that are attached to the rotary kiln and that are moving here in rotating direction. And here we then started to measure the flow regime. We did this for different materials without the use of internals, and here to mainly identify the different process parameters. In the second step, then we made use of different materials. We measured the heat transfer by use of these, I'd say, smart thermocouple setup. And again, without the use of internals. And in the third step, we then tried to vary the internals in number, in size, and in geometry. And we took all this information and used this for feeding our simulation that I've shown one slide earlier. Okay, let us now take a look at the results from the Flowsheet simulation. I have to say that the first part of the Flowsheet, that is the reactor, and here we are running this reactor as a batch process, and then we hand over this data to the continuously run process that is consisting of the centrifuge, the spray dryer, and the calciners. And here the process time is 2.5 hours. So that's the situation we have, and we tried to differentiate two different scenarios. One scenario, we have chosen parameters in our reactor that we finally end up with a particle size distribution of roughly 7.1 micron as the sort of mean diameter. In scenario 2, we decided to go for a coarser particle size distribution. So here sort of mean diameter is 12.8 micron, and this then is handed over to the subsequent unit operations. Now we enter the centrifuge, and here in the top you see case 1, in the bottom scenario 2. You see, due to the different sedimentation behavior of the coarser fraction, you also end up with a higher solid concentration of 19.5% compared to 17.6% for scenario number 1. That means here already we see a huge difference in the different scenarios, and the throughput is also somehow differing because combined with the higher solid loading, we also get a higher mass flow of 1096 compared to 1052 kg per hour. Now we go to the spray drying. We say that we start with the same droplet size distribution in case 1 and case 2. Now we change from solid loading to water content, and here we see that we start with 82% of moisture loading, and here we see that this is slightly less, but when you take a look at the numbers that are calculated, we see that we end up with more or less the same, let's say, aggregate particle size distribution of 120 micron in scenario 1 and scenario 2. But again, you see that, of course, the mass flow in the two scenarios are different. From the spray dryer, we now come to the calciner. I said that we also have an organic freight as part of the solid product. So 10% of the overall solids are organic residues. Here we try to get rid of the residues inside the calciner, and we also try to get rid of the moisture. So we separated the calcination into two single calcining steps. Temperature here, 700 degrees C. We start with an amount of 5% of oxygen. And then we end up with no more residual moisture and a slight reduction of the organic part from 8.5 to 5.7 weight percent. In case scenario 2, we have a complete no more residual moisture as well. And we also see that we have a reduction in the organics here as well. And now finally, the second calciner step, and here the residual moisture on the one hand, but also the total organic mass is coming to zero. But you see in the final end that we end up with two different scenarios of the throughput through the overall process. And this is exactly also what we are seeing in the real world in our production process. So by changing parameters in the precipitation or by changing parameters in, let's say, the solid liquid separation step, we can definitely influence throughput or even the morphology of our products. And this is something that we were now able to really demonstrate by help of this solids flow sheet simulation approach with the software DUSOL. And we were pretty happy that we really were able to mimic, let's say, the phenomena we see in reality also by help of this software. You can imagine that at BASF we have quite a number of also pretty interesting applications where we think that this solids flow sheet modeling approach is of great help. And we already use this tool for scaling up a complex solid operation. And here we see that it really helps us. For example, for this scale-up project that we had carried out, we saw that we get a very nice prediction of starting parameters per unit operations that we have built in steel. And we took this in operation, and we saw that it really very nicely matches. And by this, we were able to really bring down the startup time very effectively. Here, for example, we would like to make use of this approach also for, let's say, this belt drying technique. On the other hand, we believe that for all the granulation techniques we have, it might be of great help, for example, to mimic here the fluidized bed spray granulation and lots of other applications where we definitely see a huge benefit in the future. And this brings me already to the end of my talk. So in my opinion, solids flow sheet modeling really provides very valuable insights into the overall process behavior. And we were able to demonstrate this for our zeolite process, but we have, as said, many ideas. We will have many ideas how to, let's say, duplicate this in future. Then we see that this collaboration that we have set up with DUSOL Tech and also the industry consortium is pretty helpful. On the one hand, for the development of models, but also for ensuring that we get the sufficient maintenance, because we cannot provide this. Yeah, and as I said, we believe that we finally will end up with much faster and much more precise scale up and tuning of our apparatuses and plants in the long run, and here to support our BASF internal business partners. Yeah, with this, I hope that I was able to raise your appetite towards the use of DUSOL for solids flow sheet modeling. And in case of any question, if we do have time, please feel free. Thank you.
Yeah, many thanks, dear Fran, for this great presentation, and I'm very proud to be part of this collaboration. Thanks a lot for this long-term relationship. And yeah, now let's start the discussion. There is a question from a good colleague here online. Thank you for this very interesting presentation on a very complex topic. As I belong to the academic field, I would be interested in an industry expert advice on the following point. In terms of phenomenological modeling for industrial applications? What are the main bottlenecks or weaknesses in the models, or what and at what scale? Sorry. Yeah, you can also read this chat, Frank, if you look to the chat,
Let's see.
questions, answers, and
Okay, here I see the chat. Yeah, I think it's absolutely important that you try to come up with suitable models. Yeah, I think that the quality of your model really depends the quality of the predictability of the flow sheet, and I think there you need to spend lots of time. And of course, if you only have a very rough understanding of your unit operation, then of course it's hard to really extract valuable information. And this we have hardly learned by the university collaborations we have set up. And if you also have good data that you can use for training the models, then I think you have a good strategy. So good models, good data, and carefully evaluating if the model really predicts also changes in your processes. And then I think you have a good chance to really exploit this flow sheet very nicely. Yeah. But that takes time and expertise, and here we are also collaborating with universities, because we see that there we have also let's say the experts in the software that really help us with coming up with suitable models. And we also have our own experts, but here collaboration, in my opinion, is also the key. Yeah.
yeah. Thanks a lot, dear Frank, for the answer. Yeah, any other questions? This is not the case. So, yeah, okay, then we are on the time schedule, almost in time schedule.
We are.
Yeah, thanks for this presentation. And of course, it's a very broad field. Yeah, flow sheet simulation is on the macro scale and requires, of course, calibration also from the lower scale models and
Yeah.
also
And I really have to say that also this collaboration with University in Hamburg and Düsseldorf really helps us a lot.
Thanks a lot.
I guess also in the long run, it will pay off. And we see that by applying this, we were really able to speed up also the scale up of one of our plants, and that is really lots of money that we can save here, and it nicely pays off here.
Perfect. Okay, all the best, dear Frank. Yeah, and yeah, we
Okay.
see Moritz. We will see us also with Moritz.
And
Moritz attend. Okay,
thanks for having me, Stefan.
perfect. No, Michael. Yeah, I will hand
Yeah.
over this
Okay.
time.
Thank you also from my side, Frank. Thank you so much for the nice presentation, and that you contribute to our spotlight talk today to give us the insights from industrial view from BASF. This is of course very interesting and valuable for us, and also for the discussion at the end maybe. Yeah, and we would like to continue now with the next presentation. We shift now from gas solid flows to gas liquid flows. And our next presentation will be given by Frederic Augier. And Frederic Augier is chemical engineer at EFP Energy Nouvelles in Lyon. Huge research institution in France, as you probably know, but not only research, also industrial. So now we are in between industrial and academic research. And Frederic was also 4 years in industry at Rodia's R&D center, responsible for polyamide intermediates. And now he's, since a long time, also a participant in our working party of multiphase fluid flows. And therefore, I'm very happy, and it's an honor that I can introduce now Frederic Augier. Frederic, please, stage is yours.
Thank you. Thank you, Michael, for your presentation. Do you see my screen?
Yes, perfect.
Yes. Okay, so good morning, everyone. Thank you for your invitation for this presentation. So I will talk about bubble columns, and with a scale up about focus about scale up modeling, and some thought about similarities with 3D beds. And it's also a work I had with the help of my colleague Mathieu Morin, which is more expert than me on 3D beds, and I'm more working on bubble columns for my side. So this is the summary of my presentation. I will introduce the use of bubble columns as chemical reactors, and propose a general overview about hydrodynamics inside the bubble columns, and I will focus on some flow heterogeneities, also illustrated by some studies that we performed here at IFP. Then I will talk a little bit about CFD modeling of the bubbly flows and double columns, and I will finish with an attempt of analogy with between fluidized beds and double columns. So, as you probably know all, bubble columns are very, very popular in the chemical industry for different reasons. They have moderate to high transfer performances, mass and heat transfer. So gas phase is almost plug flow, which is generally a good point. The major part of the volume is filled by the liquid, so it means that if you need a long residence time of the liquid phase, you can achieve this with a bubble column. It also means that you are dealing with rather slow kinetics, or that you need large thermal inertia in the reactor to dilute the heat of reaction. But the main reason of this popularity is that they are very simple and cheap compared to other reactors. So these are basically an empty column. So it is cheap, and many times it's sufficient to achieve what we want to do. I have written here a list of applications that I have seen, but probably it's not exhaustive, and we can add many more. But it is very used for oxidation of hydrocarbons. Also at IFP, we use bubble columns for oligomerization of ethylene. But also for we know that they are that also used for other applications as ozonation, wastewater treatment, also hydrogenation, and also we can use them for aerated fermentations. Of course, we can add some internals if we want to promote one behavior, like the plug flow behavior of the liquid phase, or if we want to promote the mixing at low gas flow rate, we can add a tube inside and so on. But in this presentation, I will focus on the classical empty bubble column with no internals. Before to talk about flow regimes and hydrodynamics, just a few words concerning the instrumentation we can use inside, because it's not so easy to characterize bubble columns due to the presence of many bubbles. So the flow is opaque, and we cannot use classic PIV techniques or Doppler methods. So we have to use a generally more simple methodology. I have put in the red here the instrumentation that we use at AFP, but we can find many of other techniques. Concerning the gas holdup, we can use a pressure drop or liquid level measurement for the global gas holdup measurement. But if we want to have a more local gas holdup measurements, so gas volume fraction, we can use optical probes and measure the phase function at different locations in the column. But also we can use other techniques like X or gamma, or even electrical tomography for this purpose. Concerning the bubble size, we can use photographic measurements, but if we are outside the column, we will only see the bubbles close to the walls. So after that, if we want more local measurements, we can use endoscopic probes, or in our case, we use optical probes. And we know that for optical probes, there are different techniques, like the multi-probe measurements techniques that are used on the assumption that we have some vertical trajectories of the bubbles, and we can calculate bubble core distribution with them, but only if the assumption is reached. I will come back on this point, especially for the heterogeneous regime. In our case, we prefer to use a in-house method that I will also introduce after. For the liquid velocity, it's very difficult to to measure turbulence and to characterize the liquid velocity due to the presence of bubbles. So we can see some papers using hot wires or films, but they are limited to a few percent of gas, let's say at least no more than 10% of gas fraction. In our case, we use Pavlov tube. It's a modified pitot tube, so it's a pressure drop measurement, and we use it to characterize the average liquid velocity, but it's hardly usable for turbulence characterization. And for the gas velocity, we can also use some optical probes with assumptions explained before, but also we plan to use very soon some Doppler probes for in the bubble columns. So it's also well known that we have different flow regimes in the bubble columns depending on the superficial gas velocity. And when we are at very low gas velocity, we are in the homogeneous regime. It's a regime where we have no gradient of velocity, no gradient of gas holdup in the column, and the bubbles just go upward very quietly. All the bubbles are more or less the same size in this regime. And if we go to the other side, if we are at high gas velocity, we are in the heterogeneous regime characterized by a bubble size distribution, some also instabilities of the flow, a long, very large recirculation of liquid inside the column, and a lot of turbulence also in the column. And in between these two regimes, we have this transition that can take different shapes in the column in terms of gas fraction. Also, we can have some roll-up during these two regimes, depending on the Sparger geometry first. It's known, for example, from this work of Zarnik, that if we use a very, very homogeneous distributor, we can increase the range of gas velocity and stand in the homogeneous regime. But if we use a more, let's say, industrial sparger or like a perforated plate, we will achieve the transition and the heterogeneous regime much earlier at a lower superficial gas velocity. Also, this transition is also yes, a question of physical properties between gas and liquid. If we have a highly coalescent system like pure water, the transition is very early. But if we decrease the coalescence in the system by adding some surfactants or even electrolytes or alcohol, we will stand a little bit longer in the homogeneous regime. If you are interested in the transition between these regimes, which is not the focus in my talk, I can give you some references as here from the group of Haldane, also the group of Nedelchev, and also some recent works of Milano with the Giorgio Besani and Fabio Inzoli that propose some criteria to predict the resin transition. Concerning what we do here at IFP, we focus more on the heterogeneous regime because these are the regime that we have mainly in our applications, and I will go more in details about this heterogeneous regime. So this is a classical movie from a heterogeneous regime. We have a 15 centimeter per second of gas. It is air in water. You see how turbulent is the flow and also the structures of the inside, very unstable. So what we have done during the last years, we have tried to compare the flow between different bubble columns of the same geometry with exactly the same tap water and the same perforated plate used for the gas injection. And we have investigated columns from 0.15 to 1 and 3 meters of diameter just to see the effect of the scale up on the flow. And this is the results we obtain concerning the global volume fraction. You can see that we have only a small effect of the column diameter. but we have a very strong effect of the superficial gas velocity. We are very early in the heterogeneous regime using this simple sparger. An interesting point is the exponent on the VSG that I will talk after when we will compare with the fluidized beds. Another point interesting is that all this, if we look at the profiles of the gas fraction in the column, they are all similar at different scales and for different gas velocity. If we normalize these profiles by the average gas volume fraction. So when we are in the heterogeneous regime, the hydrodynamics of the gas phase is very similar, whatever the scale of the column. Concerning the liquid velocity, also we did the same characterization using the Pavlov tube, and we have the same conclusion that all these liquid velocity average profiles are all similar when normalized, this time by the liquid velocity at the center of the column. So you see these results for columns of different sizes. This is only some samples of results. But if we normalize the liquid velocity, we have always this parabolic profile. But the liquid velocity at the center is changing a lot with the scale, because it's mainly a question of VSG, of course, but also with a very, very high effect and large effect of the column diameter on this velocity profile. Concerning the bubble size, we wanted to characterize the bubble size at these different scales to see the effect of the scale up. As I said briefly, classical multiprobe techniques are based on the assumption of vertical trajectories of bubbles, which is not the case when we have heterogeneous, when we are in the heterogeneous regime. And some bubbles are coming from the side of the probe, so it's very difficult to calculate a bubble size distribution and even a chord distribution. So we have proposed to develop a new techniques which is based on the use of two optical probes, but not using the assumption of the trajectories of the bubbles. Only we measure only the spatial cross correlation between the two probes, which are located at the same level in the column. So let's consider that we have this small distance between the two probes, which is basically a few hundreds of microns, and the biggest the bubble compared to this distance, and the higher will be the cross correlation between the two probes. It means that if one probe sees a bubble and is inside the gas, there is a large probability that the second probe is also in the gas. But if now this bubble is small compared to this distance, the cross correlation between the two probes will be much smaller. And we have calculated theoretically that there is a correlation and there is a link, a strong link between this correlation coefficient and the ratio of size between the distance and the radius of the bubbles. We have validated this technique comparing the measurements with some endoscopic pictures measurements. If you want some more details on that, you can see the work of Raimundo. It was based on the collaboration we had with the Légy laboratory and the small company A2PS sensors, which produces and built these probes. To resume, also what is possible with this technique, we cannot achieve the bubble size distribution or even the bubble chord distribution, but we are able to measure the Sauter diameter inside the column, and we can do this in any regime, in any flow regime. So we are very confident with the Sauter diameter measurements, but we have no information about the bubble chords. So we have applied this technique to different bubble columns of different sizes and different gas velocities. And you see the results here concerning the average Sauter diameter in the column. We have only a very small effect of the VSG on the Sauter diameter. And we have almost no effect of the bubble column diameter on the bubble size. It is the same for the radial profile of bubble size in the column, which are parabolic. We have a little bit higher total diameter at the center due to the coalescence, but basically we have no effect of the column diameter on this total diameter of bubbles. So it is an interesting result for the scale up of the reactors. And at this stage, we have also tried to investigate a little bit more the heterogeneities that we have in these bubble columns, and we have tried to answer to 3 questions. The first question is, do we have some clusters of bubbles inside the bubble columns when we are in the heterogeneous regime? The second question is, what is the effect of the heterogeneous regime on the bubble size distribution? What can we say about that? And can we estimate also the relative velocity between the gas and the liquid in this regime? So for the first question, what we did different studies, but I will just report one. It was using also the same technique of cross-correlation between 2 probes, but now we have increased a lot the distance between the 2 probes, and we have a distance of different centimeters, several centimeters between the 2 probes in the column. And we have also looked at the cross-correlation between the probes. And if we have a cross-correlation higher than the gas volume fraction in the column, it means that we have some structures and organized structures in the flow at this scale. And this is what we see here, that we have a cross-correlation that is higher than the gas volume fraction, even at some centimeters, which is a scale much larger than the size of the bubbles. And we have done this characterization of cluster size at different conditions of gas velocity and for the different scales of column. And we see that we believe that we have clusters of 3 to 5 bubble diameters in the column. And these clusters are probably responsible of the structure of the flow and the instabilities of the flow, because they are going very fast in the column. And we can see some of them in the pictures. If we look carefully, we don't see, we see that we have some area where we have high concentration of bubbles locally. The second question is about the bubble size distribution that we have in this heterogeneous regime. So as I said before, it's difficult for us to measure something quantitative apart the bubble size, apart the total diameter. But anyway, we have tried to use these conical probes that are also done by I2PS company. We know that it is risky because we can have some errors on the results, but this is the best we can do. So we have also tried to measure the bubble curve distribution in the difference regime. So you can see the results in terms of bubble curve distribution in the columns of different sizes, and for small gas velocity, so 3 centimeters per second, we are in the homogeneous regime, and for higher velocities. And we see that at all scales, when we are in the heterogeneous regime, we increase the range of the chord size distribution, and we can see some bubbles of 2 to 3 centimeters of diameter. But their probability is small compared to the average size. So yes, we see some big bubbles in the column, but they are not sufficiently representative in terms of volume fraction to impact strongly the total diameter. So it doesn't change a lot the total diameter, but we have some big bubbles. So we are very far from the classical representation of the heterogeneous regime. For example, if you look at the papers of Chen or even other papers, a lot of them represent the heterogeneous regime in the bubble columns with very big bubbles inside, or bubble caps. And concerning our work, using the tap water that we have in Solèze, we don't have these big bubbles. We have bigger bubbles, but there are only a few. and they don't change the Sauter size, the Sauter diameter of the bubbles. So this is a big difference between our results and what we can find in the literature. The last question about heterogeneities was about the relative velocity. Can we estimate this relative velocity between gas and liquid? So to do that, we use the liquid velocity that we measure with the Pavlov tube inside the core region of the column. So the region where we have a upward flow of the liquid. And for concerning the gas velocity, we don't measure it yet. So we estimated that it was basically the average velocity of gas was deduced from the total gas flow rate. And we consider that the total gas flow rate passes inside the core region. This is an assumption, but if we use another assumption, we increase even more the relative velocity. So this calculation is, let's say, it's an underestimation of the real relative velocity that we may have in the column. And what we see if we do that, we see that in this part of the flow, we have relative velocity between gas and liquid, which is very, very high, up to 1 meter per second. And we are very far from the terminal velocities of the bubbles. So let's say 22 centimeters per second for the average Sauter diameter. And we are much higher. Even if we consider the biggest bubbles that we have measured with the conical probes, so these are bubbles of 2 or 3 centimeters, even if we consider this size, we know that the terminal velocity of these bubbles is approximately 30 to 40 centimeters per second, but we are always very far from the relative velocity that we have estimated here. So the conclusion of this part is that the heterogeneities induce high gas velocities in the reactor, in the column. This is not explained by the bubble size, and we believe that this is the effect of the clusters and the local heterogeneities of density. So we believe that it is more something related to Rayleigh-Taylor instabilities due to the difference of density locally in the bubble column. So now just a few words concerning the modeling of the bubble columns. What we did here at IFP was to consider the use of two fluid models, like 3D unsteady two fluid models using Rens turbulence modeling. When we are in the heterogeneous regime, we cannot do more than that because we have billions of bubbles inside the reactors, especially if we investigate industrial sizes like a column of 1 meter of height and like some dozen of centimeters or more of diameter. So we have billions of bubbles. We cannot do more than using a two fluid model. When we do that, we have many possibilities in terms of closure laws, and we'll just say briefly that there are different recipes possible. We see also that some different groups propose different closure laws and found some similar results. So just before to talk about closure laws, I have to say that there is no consensus on them. And I'm still not sure that I propose the best recipe to simulate bubble columns, but this is what we found as good solutions. So first, there is the question of the bubble-induced turbulence. So how can we include the turbulence induced by bubbles? And also, how can you include the energy transfer between the gas and the liquid phase? So we did different studies on this, and we found that at the end, this part of the closure laws is not essential, doesn't change a lot the results. This is what we find from our work. The more important thing to do is to adapt the drag law to include the effect of the gas volume fraction on it. So we use a drag law with the Tomiyama drag law plus a swarm factor. And concerning the other forces like added mass, lift, turbulent dispersion, and so on, we have found that we have only small effect on them. So we decided to not include these forces. But to be honest, I know that some other people say that we absolutely need these forces. We had a lot of discussion with David Fletcher, especially from Sydney, and we did not understood why in some cases people found that we need BIT and lift and so on, and why we did not found it. So I stand very prudent and take some caution about this part. So anyway, what is important to do, I think there is a consensus on that, is that we need to modify the drag law, and we need to include the fact that at a given gas volume fraction, there is a very strong decrease of the drag law, of the drag force, due to the structure of the flow. So we use the Swarm factor of Simonet, which say that we have a very strong loss of drag coefficient after a given gas fraction. And we had some good results with this, and this is something also found by McClure. Gemello was our student at AFP, and also some work of Varallo, also using the same drag law. And if we use this, we had very, very good results concerning the estimation and prediction of the gas holdup in the column at different scales. We have also good prediction of the gas holdup profiles in the columns and liquid velocity profiles. This was a part of the collaboration we had with Politecnico di Torino. And we validated this model at different scales from also for all the scales we have investigated experimentally. Now, I will take a few minutes to talk about some attempt of analogy with the fluidized bed. And this is also why I prepared this part with Mathieu Morin. So concerning fluidization, of course, we have many differences with the bubble columns, and the first of them is that we know the particles that we put in the reactor. Normally, we know their size, we know their shape, and this is a very important difference compared to the bubble columns. Another very important difference is that we are governed by the particle collisions. Let's say the granular temperature in the fluidized bed. And this is something that we generally don't consider, and the collision between bubbles is not so important to consider in the modeling of the bubble columns. We have very small particular Reynolds number compared to bubbles. And also for the fluidization, we have many subcases depending on the size and the density of the particles we are considering. So you have this famous classification of Geldart, depending on the size of the particles and the density. But generally at IFP, we focus on the class A and B because they are closer to the catalyst that we use in some applications. Depending on this classification, you can achieve some different regimes, and also depending on the gas velocity, the gas flow rate we have in the fluidized bed, passing from a fixed bed to a very homogeneous particulate regime, close to the homogeneous regime of the bubble columns. And if we increase the gas flow rate, we achieve bubbly regime and even turbulent regime, and after we have pneumatic transport. So this is very similar to bubble columns because we see that also in some kinds of bubble columns, at low VSG, we are in the homogeneous regime. And if we are at higher VSG, we start to have big bubbles, even if they are not so big in our measurements. And we are very, very turbulent. Something also interesting in that depending on the classification of the particles, so Geldart class A, B, C, and so on, we can have a difference of transition between the smooth regime, so the homogeneous regime, and the bubbling and turbulent regime. The smaller the particle, and the longer will be the homogeneous regime. And if we use bigger particles, we will achieve turbulent regime much faster. So it is very similar in terms of macroscopic behavior. It is very similar to the bubble columns because if we have big particles, we promote the heterogeneous regime. And in case of bubble columns, if we promote the coalescence in the system, we have bigger bubbles. and we are going very faster to the heterogeneous regime, and the transition between heterogeneous and homogeneous regime will be achieved at lower VSG. Now, if we look more quantitatively on the effect of the gas velocity on the volume fraction of the gas and the solid, we can also find something interesting. In this example, I have used the data of Hilal and Goon. So this is a fluidized bed using different particles. And I have just looked at the glass beads of 300 micron. And I have calculated the gas volume fraction occupied in the fluidized bed at different VSG. And in black, you have here the results of gas volume fraction for the fluidized bed of glass particles. And you have this power law behavior. And something very, very surprising that if I look at the exponent on VSG for the gas volume fraction, I have found exactly the same than the one already characterized for the bubble column. So, of course, the gas volume fraction are not the same, especially here, because when we start the fluidization and when we start to put gas in the fixed bed, we have already gas volume fraction due to the porosity between the particles. But it seems that the effect of the VSG is very similar in relative. It means that when we increase the VSG, the gas velocity will increase a lot. It will be not proportional. It will the gas velocity will increase a lot. So it says that we have also need a swamp factor, and we have a decrease of the drag law in both cases to explain these results. And to finish, this is just some remarks concerning comparison of physics at very small scale. I think that if we are going to the micro scale and looking at the interaction between the continuous phase and the inclusion, the particle or the bubbles, I think that we have very important differences between bubbly flows and particles, fluidized particles. Because when we are in the case of the bubbles, we know that due to the centrifugal forces, if a bubble crosses an eddy, it will tend to accumulate at the center of the vortex. This is, for example, an example of the work of Hock. The bubbles are going inside the center of the vortex, and we can accumulate the bubbles at the center of the vortex due to the centrifugal force. In the case of particles, this is the opposite. And you see for the same reason, we have particles are ejected from the vortices. And this is an example of injection of solid particles in a von Karman alley. And we see that depending on the Strouhal number, we have the particles that are ejected of the eddies and accumulate at the outlet, at the outside of the vortices. So to say that at a given scale, there are very, very important differences of behavior between bubbles and particles, and at a given scale, we will not use the same closure laws and the same forces, or we not see the same behavior at the scale of the eddies. So the conclusion of my talk is that we have seen the regime transition between homogeneous and heterogeneous regime. It is still not clear to know what is the first reason of this transition, if it is bubble clustering or if it is bubble coalescence. On our side, we believe that the bubble clustering is a mechanism that plays a very important role in this transition. We have proposed some recipes to simulate the bubble columns with CFD modeling. It is crucial to change the drag force, even if it is something very empirical and not completely satisfying, but it is the only way to achieve good results. Concerning the comparison with gas fluid fluidization, for me, there are important differences at microscopy scale, but surprising analogies in terms of regime transition and global swarm effect. at macro scale. So as we have seen, the same effect of the VSG. And for people more interested by this analogy between these two flows, I have found two interesting papers. One from Krishna, another one from Grace and Mostofi, and who tried to compare hydrodynamics between fluidized bed and double columns, and to propose also some CFD modeling using the same let's say same framework for both cases. So that's all for me, and thank you very much for your attention. If you have some questions, we'll be happy to try to answer.
Yeah, thank you so much, Frederic, for this nice, impressive presentation, and especially for the last part of the presentation where you compared the two different kinds of systems, and this will give us a lot of inspiring for the final discussion, I guess. Unfortunately, we're a little bit behind time, so this is why I would like to refer Alain Linet to the Q&A. And also maybe we can discuss your question, Alain, at the end of the presentation. So, and therefore, thanks a lot again, Frederic. Yeah, we will please stay online. we will discuss the presentation at the end. And with that, yeah, Stefan, would you like to introduce Rens Compost?
Yeah, of course. Yeah, the general introduction is to say that we are happy and proud to have a contribution from TU Delft, from the group of product and process engineering led by Professor Ruud van Oom, and there's also Associate Professor Gabriel Meesters. And today it's a great honor to hear Rens Compost's work on this tomographic or nuclear technique for detailed investigation of cohesive particle flows. And Ruud explained that you are so deep in this topic that you need to present this talk. Yeah? Though he mentioned it makes no sense if he gives a contribution. Therefore, we are very proud to hear that what Rens has done and will do. And yeah, I should be fast. Yeah, though, dear Rens, it's yours, the audience.
Yeah, well, thank you so much for this introduction. This is a lot to live up to. I will try my best. Yeah, so indeed, I'm here to present the work that we do over at TU Delft in the group of product and process engineering. And indeed, I'm going to talk about nuclear techniques for the detailed investigation of particle flows. And something I immediately want to highlight is among the list of authors here, I put myself first because I'm the presenter, obviously, and because I'm a bit vain. But the second author here, Christian van der Sande, is responsible for a lot of the work as well. So I really want to highlight him. And of course, both of us work with Gabi Meesters and Ruud van Oom, who are the principal investigators in our group. Okay, so what I first of all want to highlight is the need for nuclear techniques. So here you have two videos of more conventional techniques. So we have a transparent vessel where we can look at powder flows just by, well, essentially just looking at them. We can look into a horizontally stirred bed reactor on the left, or even you can use the classic semi-2D systems that we see on the right here if you want to study bubbles and things like that. And I do by no means want to discredit either of these techniques for visualizing what happens in a particle system. I think these things are really useful. What I hope to highlight in this talk is that nuclear techniques can be a really nice supplement to data that can be obtained in a more quote-unquote easy way. Because as is highlighted in this slide, particle systems are opaque. You cannot really look through the particles visually, which means that essentially what we are looking at in both of the videos are just the walls. And therefore we are more studying wall effects than actually the bulk behavior of the powder. So this is the main thing I'm trying to convey with this presentation, is that the nuclear techniques allow for a lot of nice insight into the hydrodynamic behavior of particles. And the way I want to show this is by using two case studies that we did over here at TU Delft. We used X-ray imaging, so the video on the left, for the investigation of particle flows or fluidization behavior of cohesive powders. So that's the first topic I'm going to discuss. And then in the second half of the talk, I will be discussing radioactive particle tracking, which we used to study a horizontally stirred bed reactor that is used for the production of plastics. So both of these techniques will be highlighted in the form of a case study. So first of all, about the X-ray imaging, I don't want to belabor the technique itself too much, but we are extremely lucky over here at Delft that, well, you can see it, but I can. Literally outside of the window here, we have a nuclear reactor, which allows us to use a lot of facilities. In there, what we have among a lot of things is this X-ray setup where we have 3 sources, 3 detectors. The yellow cone in the videos, you can see 3 of those yellow cones. They are the X-ray sources. And then right across from them, we have detectors. Those are the square plates. Then we put the nice image of a fluidized bed. We already imposed that in there. And essentially, the way that these measurement systems work is we send X-rays of a given energy through a system. We send it towards the detector. We place our object of interest in between the source and detector. And the detector measures the amount of energy that actually reaches the plate. Now, the loss of energy that happens while the X-ray travels from the source to the detector, that is directly correlated to the density of whatever was in between the source and detector. And therefore, what you get is essentially an X-ray shadow that is cast on the detector plates, from which we can get a lot of information on the insights of what's happening inside the system that we are trying to study. Now, that's a lot of words. What is a lot more useful typically is just looking at an image. So here's again on the left the setup that we have. We have a source, we have our fluidized bed, and then we have our detector. And in the first case that I want to discuss, we were looking at cohesive powders. Now, there's a lot of problems with cohesive powders typically when trying to fluidize them because they are very, well, obviously cohesive. The reason for that is, of course, if you make a particle very small, the van der Waals forces become dominant. Particles tend to form agglomerates. They tend to form channels when you start introducing your gas flow from the bottom. So rather than this nice fluidization that you would typically see for larger particles, we get this if we were to look at a column, which is that a crack is being formed through the bed, and essentially the gas is escaping. There's not really that much gas-solid interaction. The particles aren't flowing around nicely at all, but there is this crack, this bypass. Now, this image, I hope we can all agree, is a really bad way of visualizing this crack in the bed because you can't really see it. And that immediately highlights the need for nuclear techniques. So here's essentially the same experiment, a bit different, obviously. You cannot exactly recreate the channels. But with X-ray imaging, we can look into the system here, and we can very clearly see the bypass running through the left bit of the column here, which essentially means that our gas is flowing around the particles rather than really interacting with the bed. Now, what we are trying to do in the research, this is what my PhD was on mostly, is trying to find ways to nicely fluidize these kind of powders, which, as you can see, do not fluidize just by using conventional setups. So the first thing we looked into here is using a proxy powder. So this powder with the particle size 5 micrometers kind of mimics a powder that I'm not allowed to talk about that is used in industry and has had very high potential as a catalyst. Of course, these small particles have a super large surface area. And then first of all, I showed this image in the last slide as well. We could just conventionally use fluidization, see what happens. And what happens is pretty much nothing. We get this bypass. And if we look at our pressure drops, I don't know to what extent you're familiar with fluidization and the assessment, but usually you want pressure drop graphs to look not like this. They look like a mess. That's all you need to take away from this part of it. But then when we try to kickstart essentially the fluidization process, what we do is we shake the column. I don't know if you can see my hand. I was shaking like this, but actually we're shaking upside down. Not upside down, up and down. Pretty important differentiation there. And when we start doing that, we can see, first of all, looking at the pressure drop graph at the bottom, that we get this really nice plateau at a value of around 0.95. And this translates to meaning that it is very stable fluidization at around 15 or 95% of the theoretical maximum. The other thing, if we look at the red line, is that we can see that the coefficient of variation decreases a lot, which means that our system is very stable and homogeneous. We can also see this if we look at the X-ray. So rather than this one channel that passes through the bed, we can see that there is a nice homogeneous phase, but also we can see at the bottom there's a bit of a denser phase going on. So if you look at the epsilon scale bar in the side, the blue stuff is all gas, and then the deep red stuff is all solids. We can see that when we go down through the bed, we see essentially a section where the density has increased quite a bit. And this is something when we use mechanical vibration that we kept seeing over and over again. This is very reproducible. And when we calculate the solid fraction in that bottom section, it turns out that at times you can have about 60% of your mass present in that bottom compacted section. And it took us a while to figure out why this section exists, essentially. It wasn't immediately obvious to us. But this is very much a result of the nature of cohesive particles. So because they are really small, they typically tend to be very compactable. And what we are doing with the fluidization when we are moving our column up and down is essentially we are slamming into the powder bed with the distributor plate at the bottom all the time, creating this really dense zone at the bottom. And now this is for typical powders not necessarily a problem, but when you move to type C cohesive powders, because of their compactability, you get this kind of cake layer forming at the bottom. And ideally, of course, you want your system to be completely homogeneous, so this is not perfect. And therefore, we try to look at different ways of assisting this fluidization, essentially kickstarting this nice process as well. And the first thing that we then looked at, which was just essentially the easiest thing we could do, is rather than changing anything about the system itself, like a vibrating table, we thought maybe we can just change the way of operating the system. So we looked at pulsed flow. Now, of course, we didn't come up with any of this. This has already been studied in literature. We're just applying our X-ray imaging to stuff that already has been done to see if we can get more insights. Now, first of all, we only just look at the gas. So essentially, pulsed flow is we're constantly changing our gas velocity. So we have a high pulse, hoping that this has enough potency to break these structures, the channels that we see in our bed. And as long as we're consistently breaking them, we get this nice fluidization. Now, just looking at the pressure drop graph for a small column, this one was 9 centimeters only diameter. We see we have fairly nice fluidization, not as good as the vibrating table, but also what we can see, and this is, I don't want to overhype it, but this is probably my favorite video of the entire presentation. This is in slow-mo. But what you can see is when we are increasing this gas velocity, you see this wave running through the bed like lightning at the bottom. I think this is incredibly cool because you can kind of feel or grasp the amount of energy and the disruption that is happening through the bed there. And this is essentially what is keeping the bed fluidized, because we are consistently breaking any channels that are being formed at the bottom by putting a wave of pressure through it, essentially. So this was really nice when we did it in a small column, and we thought, yes, we found it. Easy operation. People have been reporting on this, and we just confirmed that it really works. We can kind of show how it works as well. But you feel it coming probably. There's a bit of a downside to this as well, which we found when moving to larger columns. So here we have a column that's 20 centimeters in diameter. It's about half a meter tall. We're only looking at the top section here because it doesn't fit all the way on our detector plates. But what you can see is that over time, preferential pathways still start to form. You can see these denser sections. And rather than really nice fluidization, we essentially have these fluctuating channels that are happening. And it took us a while to figure out why this is occurring, because it worked so well in the small column. But putting in a bit of thought and some brainstorming, we found out that essentially we could actually see this in the video of on the slide before already. What is happening when the wave of gas passes through the bed? Essentially, it slowly dissolves into the bed, which means that the potency that it has to break channels and structures and things like that, it's kind of decreasing with bed height. Now we assess this by taking the Fourier transform of the pressure at several bed heights, and indeed we see that the peaks that you find keep decreasing. So essentially meaning we are losing the potency to break structures, and therefore a taller bed can still form structures like this. Now we are in the Faculty of Applied Science, and especially Gabri Meesters is always focused on trying to scale up processes and making them fit for industry. So we decided to abandon this line of research in favor of looking for things that are more scalable. So this works really well on lab scale, but essentially we thought we're going to try something else for the for the larger scale operations that we hope to at some point facilitate. And then something we thought of, which we had been theorizing before, but there's not a lot of literature on it, only a couple sources, is mechanical agitation, which is just a fancy word for steering, obviously. And we thought if we can put a steerer in the bed, we can push powder around. And essentially, as long as we're breaking those structures that are otherwise being formed at the bottom of the bed, we can keep the bed fluidized. Now, as you can see, these are the first experiments that were did. We are not very creative people. So we essentially just put a slab on a stick and started to rotate it. And then when we thought that we were being absolutely wild, we put multiple slabs on a stick, so essentially forming an 8-bladed steerer, and we started to rotate that just kind of to see what happens. I'll just show you the video, and I want you to especially look at the one on the left, so the 2-bladed steerer, because the way that this works is kind of like a blender. You can see the bottom face is getting chopped up, essentially. And then now, right here, we have a bit of an overshoot at the start of the fluidization. The bed contracts a bit over time. But you can see this works really nicely. We are, in this case, physically destroying the structures that are starting to appear at the bottom of the bed. And as long as we make sure that the gas cannot pass through any bypass, but has to interact with the powder, we can keep it nicely fluidized. I know this is all fast forwarded. We did these experiments for a fairly long time. I think off the top of my head, 15 minutes. And the bed remains fairly constant. The density remains fairly low. We get even nice bubbling, which we didn't see for other types of assisted methods. But then if we move on to the steerer that we see on the right here, you can see a completely different picture, which is a very dense section near the column wall. And then a bit of a bypass, essentially just one large channel in the center of the column. And it took us, again, we're not very smart people. It took us a while to realize what was going on here. And essentially, it turned out that when you start blocking a lot of the gas by itself just wants to find preferential pathways, which is typically going to be the center of the bed. So this 8-bladed steerer blocked about 30% of the cross-sectional area of the column, and therefore blocking enough that the gas rather would just find a way to go through, and essentially it creates this spout, this channel for itself. Now to try and be a bit more creative, we decided to also move on to different kind of designs. So here are two of the ones that we studied. So a helix design, and then later we modified it to a slanted helix design. Now this helix design is already used in industry for the mixing of dry powders. So we hoped maybe we can make a bit of a translation between the two kind of systems there and use this helix to nicely fluidize our powder. And then when we had to design all of these, we decided to 3D print all of them because essentially what we wanted to do is make them modular, essentially a bit like Legos, that we could mix and match them. And probably my favorite result of the entire PhD is the picture that's up next, because the best thing about 3D printing is that you can ask them to do it in about any color that you can think of. So our lab looks extremely pretty right now, and this is my proudest achievement possibly in life. Anyway, let's talk a bit about the results here. First of all, the helix design that we used, which again we got from literature already, turns out doesn't really work. If you look at the list of images here, you see essentially the same as with the 8-bladed steerer from the last slide, where you get these dense sections at the outside of the column. And essentially, funnily enough, we made exactly the same mistake here as with the 8-bladed steerer, because if you think of a helix and look at it from the top, you will see that it has a solid outer ring of plastic, which means that regardless of the full rotation, regardless of the position, gas is always being blocked near the edges of the column. And therefore, you get these dense sections. There's essentially no gas flowing through there. And that is how we got to that spiral design that I showed in the last slide as well, which works a lot better. It's not blowing as much, not blocking as much gas. But the downside to the spiral design here is that it kind of functions as a conveyor belt for the powder, and we keep pushing powder into the center. You can see that there's some denser sections appearing near the center in these cases. At the time that we were working with this, I was blessed with a master student, very smart, Anna Bakker, and when we were going over the data here, she made a remark that, well, if we can push the powder into the center, well, maybe put another spiral upside down on top and redirect it outwards. Now, I'm not too proud to admit that I thought that she was making a joke, and I laughed at her, but I shouldn't have, because as you can see here, this is about the best thing that we ever tried in regards to the mechanical agitation study that we did. So kudos to Anna Bakker. Really need to highlight that. And essentially, it is just what she said. Like, we were still directing. If we look at the images frame by frame, you can see we are still directing powder into the center. But then when it reaches there, we are redirecting it outwards. And essentially, this makes for this very nice fluidized bed. And of course, with the benefit that we don't have those denser sections that we had with the mechanical vibration that we were using before. And also, we think, although we haven't tried it at all of the scales that we have available here, we think this has to be fairly scalable. But I cannot give any promises on that. For now, we stuck with 9 centimeter columns for this one. Okay. That was the part on the X-ray imaging for the cohesive powders. Now we're going to move on to a completely different topic and also a different case, which is the radioactive particle tracking. So a bit of an introduction of this project. This is the stuff that was mostly done by the other author, by the way, Christian van der Sande. He worked with SEBIC, and among other things, they produce plastic. Now, plastic comes in these small pellets, so small beads that you get. And the way they are produced is by introducing a catalyst to a horizontally stirred bed reactor. The catalyst moves in this image left to right, and a monomer is sprayed on top, which then starts forming this polymer beads on the catalyst. Now, the monomer has a second function being sprayed on top, is that it acts as a quenching liquid, cooling down all of the particles below, because the reaction is highly exothermic. So what we want to study here, or what we need to make sure of, is that every individual particle is cooled often enough such that it doesn't overheat, because when it does overheat, the beads start to melt together, and essentially you make one big lump of plastic in your reactor. I've been told that this happens once or twice a year, and literally the only solution here is to stop the reactor and excavate all of the plastic that is in there, because you just made one huge lump. This is just to say that the need to understand this particular reactor is of course very high for the company. But we also run into issues when trying to do that with quote unquote conventional techniques. Again, this is the video I showed at the very start of the presentation. We can see a lot here. We can see angle of repose, but what we cannot study is the individual particle movements. Now, the same is true in this case. Even though we can look at the bulk and we can see hydrodynamic behavior, we can still not see whether individual particles are carried to the top of the bed, or whether there is a lot of small vortices where particles are essentially trapped all the time when we use X-ray imaging. So both techniques are useful. Just in this very particular case, we need another tool to study what we're trying to look at, and that's how we get to the radioactive particle tracking. So the concept of the radioactive particle tracking, well, in theory, it's not too bad or too complicated. You essentially need a radioactive particle and a way to track it, obviously. Now, first of all, for the particle, unless you are blessed or cursed, depending on how you look at it, with material that is already radioactive or can be irradiated, you will need to make a particle that can be irradiated. So our particles were the plastic pellets here. Now we cannot make them radioactive. So what we did is we made a tracer particle that we try to mimic the particle properties of the bed as close as possible. And then we drill a very, very small, tiny hole in the particle. We put some radioactive gold foil in there, and then we can track it. So the way the tracking works is that we have 3 detectors that are essentially all covered up by lead plates, but the lead plate has a slit in it from which radiation can, of course, travel through. And then, as you can see on the drawing here, depending on the height and the width of the line that we see, so the height is the position, and then the width just the width on the detector, you can reconstruct the position of the particle. And when you do that for 3 detectors that you have set up around your system, you can completely reconstruct where the particle is with a pretty high accuracy. I think the average accuracy that we got is about 5 millimeters. Now, considering that we have 1.8 millimeter particles, we're only like 1 particle off to either side in this case, which we believe is really good for these kind of systems. And in practice, it looks like this. So this is the same bed reactor that I showed you before. Of course, no reaction is going on in the case that I will present. But we have the 3 detectors. We put the particle in, and then we just rotate it for a very long time to get a lot of data. And first of all, just marvel at this video that Christian made. I don't know how he did it. It looks amazing. But we are essentially tracking that one particle over time here. Of course, it is rotating because the impellers are throwing it around the particle bed. But as visually nice as this is, probably graphs will do better, especially for papers. So what you can see here is you can take time average flow fields. You can see the direction that the particle takes when it is in a given position. You can see the frequency that it appears in certain places. You can get the velocity profile. And what you can already see if you look at the top row and then the columns for 20 rotations per minute for the impeller and the 40 rotations a minute is that just below the impeller on the left, there appears to be a bit of circulation of the particle. So that this might be a hint that the particle is not actually carried to the top. It's not cooled down in the actual system enough. And therefore, this may be a bit of a problem. I can see this a bit better if we take time average particle hold up, which you can see on the left here. So we take different fail grades that you can see on the y-axis of the rows. And here you can, again, very clearly see for the low fail grades, which is 40% of the reactor volume, and low rotation speeds, you see that the particle is actually kind of trapped in this zone to the left of the impeller, which means that there is very much a risk that the particle isn't cooled often enough, can overheat, and therefore you get this really big bead of plastic that you don't want to have in your reactor. Now put in numbers. If you look at the graph on the right here, you can very clearly see that the fill grade has an obvious effect on the particle holdup. And then also, and this is a bit more intuitive, I think, the rotation speed of your impeller obviously has an effect as well. And what you can learn from this quite simply is that a higher fill level means that your cycle time decreases. So the amount of time that the particle passes the cooling zone increases. And also that this scales in the same way essentially with the rotation speed. So both fill level and rotation speed, ideally you want to increase them to get your cooling down. Now this reactor is a bit more complicated than that because it's not a 2D reactor, obviously it's 3D. And if we look at the top for the actual dispersion of the particle, we need to think about the way that the reactor works. Ideally, it would be a plug flow. So your catalyst enters and then all of the particles leave at the same time. Very nicely, having this very nice particle size distribution that essentially is very narrow because they all spend the same amount of time in the reactor. However, what we can see here, if we increase the fill grade and the rotation speeds, I can also show that in this graph over here on the left, is we see that the actual dispersion increases, and therefore you get a bit less plug flow and a bit more mixing into your system. Now, luckily, it's not up to us to actually optimize the reactor. But if we look at the observations that you get here, it means that with rotation speed and fill grade, your actual dispersion increases. So this essentially means that it's really good for your cooling, and you kind of need it to make sure that you're not overheating your reactor. But at the same rate, you want to still minimize it to maintain your product quality. Now, as I said, luckily, it's up to the people over at SEBIC to actually figure out how to operate the reactor. But it's kind of a nice way to show that this radioactive particle tracking allowed us to look into this system and find these kind of correlations. Then finally, as a bit of a preliminary thing, you don't necessarily want to work with radioactive particles a lot. So we are also looking into ways to do particle tracking, but with X-ray, which is still not super healthy, but a bit better, at least. And what we found is that potassium iodine has a really good attenuation properties, essentially killing a lot of X-rays when it has to pass through them. So this means that if we can impregnate particles with this potassium iodine solution that you can see on the left here, so the bottom sorry, of those images is a particle on the left-hand side, just a normal particle, on the right-hand one that we impregnated. You can see that on the X-ray, it very clearly shows up. And then I can play the video on the right here. you can see that even with the X-ray, we can still kind of detect the particle. It's a bit harder. It's not as accurate as the radioactive particle tracking, but of course it has a lot of benefits with regards to the operation. And if we compare the two results that we have from radioactive and from X-ray particle tracking, yeah, we can see kind of the downside of the X-ray particle tracking here, which is essentially error bars. Like the trends kind of hold in most cases, but the error bars just become a lot bigger, which is a bit, I don't want to say disappointing, but ideally we would have kept the same trends and we would be able to capture them. This is ongoing work though. We're still playing around with the settings of our system a bit to optimize this. But yeah, that's a bit of the ongoing work. So we are still expanding our operations of the nuclear facilities that we have available here. With all of that being said, I have one big conclusion that I already spoiled in the first slides. The nuclear techniques allow for the insights into opaque systems. And then also want to highlight that this is both for fundamental research, which is more the first part of the presentation, but also for applied research. We can really do just cases. We can do case studies and apply these techniques to them. Now, for the X-ray, you get a lot of hydrodynamic insight, which can be extremely useful. And then for the radioactive particle tracking, it's really when that individual particle motion becomes important. You can get these velocity profiles. You can identify the dead zones, which especially I think is really, really cool. Coolly, that's another word, which is really nicely visualized by the work of Christian. And with all of that being said, I would, of course, like to thank you all for your attention, and I'd like to thank the organizers for including us in this colloquium. So thank you all.
Thank you very much, dear Rens, for this very, very impressive talk. Yeah, also this discussion is open. This presentation is open for discussion. So do we have any questions? Yeah, we have a question from an anonymous attendee. Very interesting presentation regarding the RPT. How does this differ to positron emission particle tracking? Good question. What advantages does RPT have over PEPT? Yeah.
Yes, I agree. This is a very good question, and this is immediately where I have to take the mask off and say this is Christian's work. So this is the part that I wasn't directly involved in. So I'm sorry, I cannot really give you the answers here. I assume he discusses it in his papers in introduction sections, but I'm sorry, I cannot give you a very satisfactory answer here.
Okay. Yeah, there are some good work which has been done in Birmingham, yeah, by the group on PEPT. Do any other question?
I see one of the temporal and spatial resolutions.
It's the temporal and spatial resolutions of technique. Yeah.
Yeah. So for the X-ray imaging we do, you can kind of play around with it a bit, but usually what we do is we shoot at 50 hertz, and then the spatial resolutions is about 200 micrometers. So that's the pixel size essentially on our detector. But you have to think about the fact here that it kind of works like a projector. So the position of your object of interest relative to the detector kind of influences the actual size of each individual pixel that you are looking at. So you can play around with that a bit, but we usually shoot at 200 micrometers per pixel and 50 hertz.
Okay, I believe we are a little bit out of time. Therefore, I would also like to stop now all these questions regarding this presentation for the moment. And many thanks again, dear Rens, for this contribution. And now we come to the conclusion, but conclusion means in our case, and Michael Schlüter is also available now, that we have a small podium discussion, so to say, about the similarity and differences of both strategies. Yeah, and question is how we should start. So of course we have all the speakers in the floor here, so to say, and Dr. Buchholz has replaced Professor Kleine Jäger because he has a very important meeting. Dr. Buchholz is a former alumni of my institute, but he's responsible for all the simulation techniques at BASF at the moment. in that direction. Question is, yeah, dear Michael, would you like to chair this session or would you like to start?
Yeah, maybe we can just use a couple of minutes. I mean, it's close to lunchtime, but maybe a couple of minutes summing up the presentations and discussing them a little bit together. So thanks all of the speakers. First, it was really impressive to see what's going on in the different areas. One point that comes into my mind is, I guess, one of the important similarities are these heterogeneous structures, right? So was something that was addressed in all presentations. And my question in this sense would be, do you think there is a similarity that goes so far that you can, for example, Rens showed the destroyment of these structures by pulsating flow. Do you think the same would be possible in a bubble column, Frederic, where we have also these kind of clusters? I mean, I know there are pulsating bubble columns. I know about that. But do you know if this has ever been studied for destroying clusters and compartments? And this brings me to the point, does the energy dissipation rate, yeah, I mean, we know from fluid mechanics that energy dissipation rate gives an influence on particle size distribution. Is this the same in solid gas flows and bubble gas liquid flows? Frederic, what do you think?
For the first question, okay, for the first part of the question concerning how to break the clusters of bubbles, yes, to be honest, I never thought about that. I think the price of the equipment will not be the same if we add agitation inside. And classically, if we use bubble columns, is that we prefer to have a very small investment for the reactor, or we don't need especially high mass transfer or something like that. So yeah, it's a very it's something to think about, but I have no answer about that. Yes, probably if we add turbulence, we can break the clusters, but does it worth to do this in case of bubbly flows? It's case by case question. I have no answer on that. Sorry.
Rens, you do not have any experience with gas liquid flow so far, right?
No, we just study the gas particle fluidization. Yeah.
Mm-hmm. I just see there was one more question in the chat from it's already answered. Okay, thank you. Yeah, any further points?
Well, just to complete my answer, classically, when we have very high gas velocities, like 20 or 30 centimeter per second of gas, it's doesn't work to use stirred tank and agitation. You see, it's too high to have a benefit of the agitation on the mass transfer. So I think we put agitation when we are dealing with lower gas velocities. And in this case, we break bubbles. Probably we break the clusters, but we break the bubbles and we enhance the mass transfer. But if we have a 30 centimeter per second of gas, probably it's not the good case to add some agitation. But yeah.
Of course, this is also a comment from my side. The scalability is, of course, of great importance in general, as you mentioned, in both directions. Yeah, for instance, fluidized bed dryers for milk powders will be produced by some companies, and they are 20 meters in length, and they are vibrating. So that are vibrated fluidized bed, so meaning that the setup is shaken and not the gas pulsates, but the machine is vibrated. And also in the opposite direction, also Ruud is working on atomic layer deposition, since many years. Alan Weimer is doing the same in Colorado. And a question is also how to deposit metals from the gaseous phase. So these reactors are used for nanoparticles, so to say, and also for deposition and coating, and could be very interesting also yeah, to go into the lower scale, okay, that is easier perhaps than to go into the larger scale. But both directions are important, yeah, also for industrial purposes, also the small scale.
And maybe one additional point to the related to the first presentation from Stefan Pirker with the recurrence CFD. I mean, you also use for the rCFD these structure and the repeating structures, and this is also very similar to bubble column reactors as far. But as far as I know, recurrent CFD has not been used for bubble columns so far. Or does anybody has another information? So Frederic, do you have seen something like that? But that might be very, very useful, right? And I mean, in principle, there's nothing against that, I think.
Yeah.
I think we historically we started with bubble columns in developing rCFD, and if you have characteristic structures, reoccurring structures, and you can describe them by your base CFD simulations, then you are a candidate for rCFD.
Yeah.
Actually, I very much liked the attempt of Frederic, so I enjoyed listening to your last slides.
Yeah, very good overview about the similarities, yeah.
So I think the relative velocity between the phases is increased by the heterogeneities. So the clusters of bubbles or the clusters of solid changes the velocity of between the phases, and that's why we have the same shape in terms of gas volume fraction versus superficial gas velocity. And I think that it is a question of Rayleigh-Taylor instabilities. If you look at such instabilities in the sedimentation domain, but after that, if we want to model it, we don't know. Probably from the particular on the gas fluidization, it's easier to model with DEM simulation and so on. But for the bubbles, we are a little bit we have some difficulties to see how to investigate this physics.
Very
And
interesting.
and two fluid models are too macroscopic to catch it, so we need to model it in the closure laws, but it's not satisfying. Yeah.
Yes, in gas liquid flows, the physicochemical properties of the interface comes into play, right? And maybe this is an additional complexity that has to be solved, and this is not so important for the solid gas flows.
And you have interfacial tension, which we don't have.
Yes,
That's a bit,
exactly.
of course, but interesting is that we also have bubbles, yeah, and also the
Yeah,
bubbles are very similar, the coalescence and also splitting of bubbles. There are dozens or more than dozens of bubble models available. That is very, very interesting. Yeah, these similarities are immense.
So what are the forces keeping your bubbles in fluidized beds together?
Yeah. And of course, there are several scaling laws also for gas solid fluidized beds from Glicksman, from Horio, from Grace. And this could also be compared perhaps with a gas solid, gas liquid system, but also perhaps for for liquid solid systems could be also interesting. Yeah, we have also liquid solid fluidized beds in the biotechnology and wastewater treatment and so on. So there's a third region, so to say, and the scaling up, meaning that certain fluidized beds have a higher height to diameter ratio. Yeah, that is well known, but there's also a limit. Yeah, as one gets slugging, so to say, if the diameter is too tail and too small and the apparatus is too high, then we get slugging, immense slugging in fluidized beds. I believe that is not as dramatic in bubble columns as in fluidized.
Yeah, that's what Alain Linné from the auditorium mentioned, yeah, that he was happy to see slugging as well in fluidized beds compared to bubble column reactors. So I guess indeed there is a similarity.
The big slugs in double columns are only for smaller diameter. I think. But not the case for fluidized beds. You can see these slugs at higher scale.
Yeah.
Yeah.
Yeah. Yeah. The largest fluidized bed which I know are fluid catalytic cracking setups, which are almost 100 meters in height. Yeah, 100 meters also for yeah crackers. Very large. Yeah, they have some meters in diameter, but not 100 meters in diameter. Yeah, so this ratio is more in the height direction. But one needs to be careful with the slugging, and also with the turbulent. Yeah, with the transition between bubbling and turbulent fluidization, there's also very interesting transition behavior, yeah, which is still not very clear for Gelder B particles. And yeah, this needs to be considered in future investigations. So we have the dilemma that we have also particles with certain yeah, density, and they behave very special with respect to their classification, their so-called Gelder classification. Yeah, so they are cohesive or also tends to form aeration-like fluidization, yeah, or bubble-like fluidization, or spoutable. So that is our criterion, yeah, or our regime mapping, so to say, yeah. And problem is also if particle systems are wet or are partially wet. If we atomize a liquid, or if we dry powders which are initially wet, sorry, then also the fluidization behavior changes. This could also be very interesting for these kind of simulations, or also for measurements. The difference between dry and wet conditions, yeah, for gas solid systems is not completely clear. So we have van der Waals forces, they are even there, but capillary and viscous forces, and these kind of forces are a bit different in the liquid systems. Forces acting on the individual elements. Of course, that was yeah. This session here was very broad. Yeah, we talked about also CFD simulation, CFD-DM, but question is also the strategy to develop compartments and the macro scale with flow sheeting and recurrent CFD is such an impressive tool to make it very fast. Yeah, to have to bridging also a little bit the gap between this microscale high resolution models, and what I never have heard from you, Stefan, about this coarse graining recurrent CFD. That is really new, and that is fascinating. Yeah. So that allows us also to go into the direction of these smart reactors. Yeah. Michael Schlüter, spokesman of a collaborative research center at our university, dealing with such kind of smart reactors, and scalability is hot topic, and the methods, also simulation methods, should be fast. Yeah. Therefore, recurrent CFD is a very interesting tool also for this kind.
Yes, indeed. So we really should try to use this also for the gas liquid flows. It's quite interesting.
Yeah.
So it was really very nice to hear that today.
The autonomous reactor concept, yeah, is what
Yes.
make the reactor in a understandable, and to have also a closed loop control, etc. And then we need these very fast predictive tools. And very interesting. My question would also go in that direction. Who is working with this AI, this machine learning tool? So this is of great importance since a few years. And yeah, also for post-processing, you can analyze your pictures, yeah, so the images after these analyses, but you can also work with data-driven or physics-based driven AI methods. Who's working with these tools would be a bit the question also. Who's
Maybe
working?
I can comment a little bit of a peek preview, sneak preview. You know, that there is collaborations going on, and I told you rCFD is one method to do this, data assisted. There are other methods out there, and in collaboration with some freaks from weather modeling, we have now used the method which is also implemented in ChatGPT, so the transformer technology, in order to model fluidized beds. And this, what comes out of this is really opening the door towards something completely new, because you can learn it by different settings of fluidized bed, and then you could throw this model to a fluidized bed which never has been trained. So with for instance, with a new superficial velocity, and you get the unsteady behavior of this fluidized bed with all these heterogeneities to a very, very high degree of accuracy. So if you look at bubble formation and everything, so this is all in the model, which is completely, yeah, data-driven.
Yeah.
So I think my prediction would be that in the upcoming years, we will see quite a lot of this,
Yes.
these methods.
That's forecasting, not only soft sensor development, is forecasting.
Yeah, you get really the four-dimensional picture of a fluidized bed is delivered for a system which the AI has not seen before. And this is, if you want, it is ChatGPT for fluidized beds.
Yes, very promising.
Yeah, but in the end, it's data-based modeling. So there was a question if I would think that AI takes over. I don't think this, because you need to feed these AI techniques in order to get the data, and so it's in the end it's just an interpolation technique. But once you have it, it's nice to have it.
Okay, any other comments? So as we all know from the particle technology field, at least, I do not trust someone who's only doing simulations and who never had done any kind of experimental test, yeah, with these powders, with these granules, because sometimes also agglomeration happens, and desired or wanted or unwanted agglomeration, yeah, and how to deal with these kind of yeah, product properties. Yeah, the particle properties can be much better understood if we have a kind of database, and then this machine learning tools might help to calibrate also this DM models with material parameters like friction coefficient, yeah, and restitution coefficient, and so on and so on, because yeah, that is strongly dependent on material properties. Yeah, this could also be very interesting.
I have one thought which was triggered by Frederic, and this was in uh, gas solid fluidization. You know, the origin, the physical origin for these heterogeneities. You can derive this for 1D by 1D dimensional considerations, and the core is that the drag force depends on the volume fraction, and you get something which is called kinematic shock waves. Have you heard about such one-dimensional considerations in bubble, also gas fluid systems? Because there were two sentences for you. One was, okay, the drag force is the most important, and the dependence of the dependence of drag force on the volume fraction, and there was this this velocity to the power of something which was similar to those. Have you heard about this one-dimensional, or are you aware of these one-dimensional considerations and kinematic shock waves in bubbly systems?
No, I know the 1D models for the bubble columns. A lot of work done on the drift flux models and so on. But I'm not so informed about what you say. And yes, the question of the instabilities you can see in 1D using 1D model directly. I don't know if Michael, you know this this approach.
No. I just write it down. I will check it up.
Yeah.
It's a good
There's a
hint.
nice book, but I've forgotten the name of this. And this starts with one-dimensional considerations of gas-solid fluidization. And he just showcased the physical origin for these bubbles in fluidized beds. And it was so real nice because you can really see the physical core phenomena, which triggers the heterogeneity.
Mhm.
And I thought maybe there is some similar phenomena.
Yeah.
Mhm.
It's interesting because it is the opposite that what I have in mind personally. I more believe that we can use 3D tools to understand physics and then to derivate it into 1D model. But it is possible to do the opposite. It is very interesting, and we have to. Yes, I will be happy to read this. Yeah, if you find the reference or something. Yeah.
Yeah.
Because
I
for
will
me,
send
the
you the
question is
reference.
clustering. I think we have a homogeneous flow. After we have some clustering, at this scale, we start to have instabilities, and the gas phase is going much faster in the column, and so we try to have instabilities and so on. But it's from micro scale to macro scale in my mind. But if we can understand physics from 1D approach, it's very interesting and probably also can change the
Maybe
flow
this is
locally. But
really
yeah.
linked to gas solid.
Yeah.
But in
Yeah.
gas
Yeah.
solid, we have this explanation from.
Yeah. Yeah, and Alain Linné has just mentioned here in the chat that listening our discussion, I remember the work of Wien Garden on kinematic and void waves in bubbly flows. So
Okay.
thank you,
We'll try
Alain.
to.
Yeah.
Yeah.
We
Thank
will,
you.
we will
Yeah.
check
Maybe.
it. We will check it.
Also, a comment or a question, yeah, from Fokat Kamitov. What do you think about PIN, a physical informed network for NS equations?
Navier-Stokes equations. So may I take over? So pins was a hot topic, but at least those guys I'm collaborating with, they have already moved from pins. Pins is a local method. You just try to mimic the behavior of Navier-Stokes equation in every point of your domain. And this what I label ChatGPT or transformer models, they look at patterns and how would patterns evolve. So this is completely different approach. And I personally, I really believe in the importance of these heterogeneous patterns. So there are investigation in gas solid fluidization about the dimensionality. So locally you have so many dimensions, so every particle can move wherever it wants. But if you look at the same situation globally, then you have the shock waves, so you have the voids which are going up. The dimensionality is far less than all these particles, so they arrange themselves. And so you have patterns, and if you are able to describe the fate of these patterns or the fate of these heterogeneities, you're able to describe the flow far more efficient than with a local method. And pins is a local method. So I'm not I don't give pins too much future in comparison to these transformers.
Okay, good statement. Yeah.
Very
Good to
good.
have on board, Stefan, in the discussion. Yeah, yeah, also a comment, another comment of Fokat, yeah, additional. Is the same good a numerical approach for gas, liquid, solid system in heterogeneous regime?
Yes,
Yeah,
liquid solid.
gas, liquid, solid, yeah, it does exist.
What is the continuous phase in this case?
Yeah, okay. But
We have
okay,
often application with catalyst particles in ebullited bed with gas also. We have two dispersed phases, gas and particles inside the liquid. Probably it exists some CFD modeling on that, but it's much more difficult, I think. So I have not seen it recently.
okay, any other questions or comments? I believe it's not the case. So, Michael, what do you think?
Okay, yeah, probably everybody's hungry now, but
Yeah.
we are very lucky that you are still here, and we still have nearly 50% participants, so very, very good. Thank you so much for the nice discussion, and also for the participants to stay so long with us and discuss with us. Yeah, and thanks a lot to the speakers for the nice presentations. And Stefan, do you have some more final comments?
Okay, final comment is that it was great to have some fresh faces here on board, or Rens. I never have seen you in real life. I read your publications. Thanks a lot for giving this talk. That was an excellent contribution.
Thank you so much. Thanks.
Of course, also Stefan is a good friend of us, Michael and Frederic, same. But my comment goes into this direction. The science is so fast, and we have seen during the last year so many new developments like AI, and also the sensor development, and also recurrence CFD was not in the main goal 10 years ago. Yeah, in the research, Stefan has developed this technique, and it's so fascinating. Although I'm very hopeful that in the next years we will not be without any work. Yeah, and of course also the transition from dense gas solid fluidized bed to bubble flows is there. Though we have also transport processes also in fluidized bed. You have transport processes which we haven't explained in a very detailed manner today in such bubble columns. We have heat transfer, mass transfer, and fluidized beds also. And this makes it very interesting in future applications also. And perhaps also a comment from our side to Rens. Alexander Penn, who was also attendee of this presentation, is a very excellent MRI, the magnetic resonance tomography, magnetic resonance imaging here in Hamburg. As the Institute of Process Imaging. You should get perhaps also in contact with these colleagues. Of course, not to have a competition, yeah, but just to compare, to have a complementary techniques which are required. Could be interesting, yeah, to compare your very impressive technique with Alex technology here, MRI.
Yeah, thank you for the suggestion. You sent some of his work in our prior correspondence, so I have it saved. I didn't read it yet, but it's on the list. Yeah, thank you. Yes.
Very active in this field. Yeah. Okay. So
good. Thank you so much again. Martin, would you like to add something?
No, just I think we are now at the end of the webinar. So thank you to all the speakers, and thank you for the participants. So we are here at quite noon 30, so just time for having lunch. Thank you, and see you in the next webinar. Bye.
Thank you so much for organization. Bye-bye.
Bye-bye. Thank you.
Bye.